This online tutorial is about solvent system acid-base definition and theory. Historically, at first, studies were concerned about aqueous solutions or solutions in which water is the solvent. Among such studies, the theory of ionic dissociation of salts in aqueous solutions and also the water-based Arrhenius acid-base theory were notable, where both of these theories were proposed by Arrhenius. Later, scientists got more concerned about non-aqueous solutions, or solutions in which the solvent is anything other than water. In 1905, Edward Franklin, who had worked on reactions of electrolytes in ammonia, pointed out similarities to acid-base reactions in aqueous solutions and the water-based Arrhenius acid-base theory. This increased the interest in developing an acid-base theory applicable to other solvents. Later, Albert German studied non-aqueous solutions of phosgene, COCl2, as the solvent and tried to develop an acid-base theory applicable to dissolved substances in solvents like phosgene, COCl2. Albert German published his idea in the article with the title A General Theory of Solvent Systems in 1925. Later, Katie and Elsie highlighted such works and tried to answer the need for a completely consistent nomenclature in this field by publishing an article with the title A General Definition of Acids, Bases and Salts in 1928. Based on such works by scientists like Edward Franklin, Albert German, Katie and Elsie, the solvent system acid-base definition and theory was developed and introduced to scientific society. What is this theory about? To introduce this theory, at first we should be familiar with self-ionizing solvents. Self-ionizing solvents can have ions even in their pure form. Such solvents produce ions by self-ionization or auto-ionization. And are called self-ionizing solvents. For example, water in its pure form or aqueous solutions in liquid state can have this reaction. Okay, so we consider that solvent is water. For water, we can consider this reaction. Where it is in fact better to write this reaction in this form. But as far as we consider that H plus AQ represents hydronium ion in water, for simplicity, instead of this reaction, we can consider this. In this reaction, we have transfer of an H plus from one water molecule to another one, yielding hydronium and hydroxide ions. In this reaction, water produces ions by itself alone. This is the self-ionization reaction of water, and water is considered as a self-ionizing solvent. Here, it is very important to consider that the extent of this reaction, and in general, the extent of self-ionization reaction of self-ionizing solvent is usually very small. For example, the concentrations of ions due to this reaction at equilibrium for pure liquid water at 25 degrees Celsius is only 10 to the power of -7 molar, which is very small, yet important in some discussions like acid-base analysis. We usually neglect the self-ionization reaction of self-ionizing solvents, but in some discussions like acid-base discussions, these reactions can be important. Water is not alone in being a self-ionizing solvent. As another example, we can consider NH3, ammonia. In liquid ammonia, in its pure form or its non-aqueous solutions, we can have this reaction. This is the self-ionization reaction of the solvent ammonia. In this reaction, one ammonia molecule donates an H+ to another ammonia molecule, yielding ammonium and amide ions as their products. Here it is good to consider that different solvents exist in different situations. For example, the normal boiling point of ammonia is -33.3 degrees Celsius. So we can't have ammonia in liquid state at room temperature and pressure, while we can have water in liquid state at room temperature and pressure. Also, it is good to consider that as we use AQ for aqueous solutions, we can use SLN for solutions in general. It is also important to know that we usually deal with aqueous solutions and water. But here, this reaction has nothing to do with water. Ammonia does this reaction by itself, alone. The produced ions are solvated and surrounded by ammonia molecules. There is no water here. Solvent is different. We see that in these two reactions, we have transfer of H+. So, self-ionization reaction of these two solvents are also proton transfer reactions. This is not generally true. Other solvents may self-ionize by other methods. For example, for the solvent phosgen, COCl2, we may consider this reaction as its self-ionization reaction. For the solvent N2O4, self-ionization reaction may be considered like this. And for the solvent SO2, sulfur dioxide, we may consider self-ionization in this way. So we see we have cases in which self-ionization of self-ionizing solvent has nothing to do with hydrogen and transfer of H+. Based on these reactions, we can see that every self-ionizing solvent produces its own specific ions in self-ionization reaction. For example, water produces hydronium and hydroxide ions, while ammonia produces different ions, ammonium and amide ions, and so on. These specific ions produced by self-ionization of the solvent are considered as characteristic ions of that solvent. In other words, a self-ionizing solvent produces its characteristic cation and characteristic anion in its self-ionization reaction. So hydronium is the characteristic cation and hydroxide is the characteristic anion of the solvent water, while ammonium is the characteristic cation and amide is the characteristic anion of the solvent ammonia, and so on. Now that we are familiar with self-ionizing solvents, we can discuss solvent system acid-base theory. Solvent system acid-base theory and Arrhenius acid-base theory have similarities. Based on the Arrhenius acid-base theory, an acid is a producer of H+, a base is a producer of OH- in aqueous solutions, and acid-base reactions are in fact reactions between those H+ and OH- ions produced by acids and bases, yielding water as one of the products. For example, in water, nitric acid, HNO3, is an Arrhenius acid because it can produce H+ in water. On the other hand, potassium hydroxide is an Arrhenius base because it can produce hydroxide ion in water. And the acid-base reaction between these substances is in this way, like this. If we omit spectator ions in this reaction, we will have this reaction, the reaction between H+ and OH- ions, which is in fact the reverse of the self-ionization of water. Here you see that based on water-based Arrhenius acid-base theory, an acid increases the concentration of H+, the characteristic cation of the solvent water. A base increases the concentration of OH-, the characteristic anion of solvent. And acid-base reactions are in fact reactions between characteristic cations and anions, yielding solvent as one of the products. Solvent system acid-base theory extends this to other solvents. Based on solvent system acid-base definition and theory, an acid is any chemical species that increases the concentration of the characteristic cation of the solvent. And a base is any chemical species that increases the concentration of the characteristic anion of the solvent. Also, acid-base reactions are in fact reactions between characteristic cations and anions produced by acids and bases, yielding solvent as one of products. For example, consider ammonia as our solvent. In ammonia, we can have these reactions. Ammonium nitrate can increase the concentration of NH4 plus in ammonia. NH4 plus is the characteristic cation of ammonia. So, based on solvent system acid-base theory, ammonium nitrate is an acid in ammonia. On the other hand, potassium amide, which can increase the concentration of NH2 minus, the characteristic anion of ammonia, can be considered as a base in ammonia. The acid-base reaction in ammonia is as follows. If we omit spectator ions, we get this reaction, which is the reverse of the self-ionization of the solvent. Here, it is easy to spot similarities between these reactions in ammonia as acid-base reactions in ammonia and these reactions in water as acid-base reactions in water. In both of them, acids are producers of characteristic cation of the solvent, bases are producers of the characteristic anion of the solvent, and acid-base reactions are in fact reactions between those characteristics ions, yielding solvent as one of products. As another example, consider the solvent N2O4. For N2O4, we may consider NOCl as an acid because it increases the concentration of NO plus in N2O4, the characteristic cation of our solvent. We can consider silver nitrate as a base in N2O4 because it produces the characteristic anion of our solvent. And we can have acid-base reactions like this in N2O4. Reactions which may be assumed as reaction between NO3 minus, the characteristic anion produced by base, and NO plus, the characteristic cation produced by acid, yielding solvent as one of products. In the case of SO2, as another example, we can consider these reactions. Based on solvent system acid-base theory, tyronic chloride is an acid in the solvent SO2 because it increases the concentration of SO2 plus, the characteristic cation of the solvent. Cesium sulfide is a base because it increases the concentration of sulfide ion, the characteristic anion of the solvent. And acid-base reactions are like these, which may be assumed as reactions between sulfide and SO2 plus yielding SO2. Reverse of this reaction. Here we can see similarities between acid-base reactions in different solvents. This is the advantage of solvent system acid-base theory. By using solvent system acid-base theory, we can talk about acid-base reactions in different solvents by the same method. And also, we can analyze acid-base reactions in other solvents in a way similar to reactions in aqueous solutions. But solvent system acid-base theory has also limitations. And those limitations are similar to that of the water-based Arrhenius acid-base theory. One of its limitations is the fact that it limits acids and bases to solvents. Arrhenius acid-base theory limits acids and bases to water. This is its limitation. In the case of solvent system acid-base theory, solvent can be anything. Of course, with the condition that it should be able to self-ionize. But after all, this is a limitation for both of them, even for solvent system acid-base theory, because we can have acids and bases in other situations, for example, gas phase. As an example, consider these reactions. NH3 and HCl in gas phase yields NH4Cl, and also NH3 and HCl in aqueous solutions yields NH4Cl again. These two reactions are almost identical, with the exception that this reaction happens in the gas phase, while this one happens in aqueous solutions. By a common sense, both of these reactions are acid-base reactions. Solvent system acid-base theory considers acids and bases in solvents. So solvent system acid-base theory includes this reaction, but excludes this reaction. Why shouldn't we consider this as an acid-base reaction? Why should our theory exclude this reaction as an acid-base reaction? They are very similar. So, limiting acids and bases to solvent is not a good idea, and this is a limitation for solvent system acid-base theory. A more important disadvantage and limitation of the solvent system acid-base theory is its emphasis on ions. Many solvents are not suitable for creation or existence of ions. And for those solvents suitable for ions, in many cases, acid-base reactions don't need or rely on ions. For example, experimental works don't support existence of highly charged SO2 plus cations in the solvent SO2. In fact, they deny it. Also, this reaction doesn't need dissociation of SOCl2 and production of SO2 plus for its execution. This reaction can happen by just these two reacting with each other, with no need for SO2 plus. As another example, consider these reactions. The first reaction happens in the gas phase, the second one in aqueous solution, and the third one in benzene, which is a nonpolar solvent, and it is not suitable for ions. These three reactions have similarities. In all of them, the nitrogen atom of the base accepts NH+. In the case of the first reaction, we don't need to assume that HCl molecules release their H plus ions to the medium, to the gas phase, and then those H plus ions react with NH3. In fact, this is not reasonable, because gas phase is not suitable for existence of ions in a lone situation. In this reaction, NH3 and HCl molecules can directly react with each other upon suitable collision. Similarly, in the third reaction, in benzene, which is a nonpolar solvent and not suitable for ions, there is no need to assume that HCl molecules release their H plus to the medium, to the solvent, and then after that, those H plus ions react with aniline, with this substance. They can react directly with each other, with no need to release of ions to the solvent. In the second reaction, most of both ammonia and acetic acid are undissociated in water. They remain in their original form. They can react with each other directly. There is no need to assume that all acetic acids release their H plus to water, and then those H plus come and react with NH3. So we see in all of these three reactions, there is no need to think that acid releases cations to the medium, and then those cations react with our bases. So in some acid-base reactions, there is no need for ions. So emphasis on ions in solvent system acid-base theory is misplaced. and we can consider this as its limitation. Here, it is also good to be familiar with some terms related to the solvent system acid-base theory. These terms are protogenic and its synonym protic, protophilic, amphiprotic, aprotic, autoprotolysis, lyonium, lyate, solvonium, and solvent. These terms are usually used for solvents. A protogenic solvent is a solvent capable of acting as a proton donor, that is, as a Brensted acid. Protic is synonym with protogenic, but protogenic is preferred to protic. Protophilic. A protophilic solvent is a solvent capable of acting as a proton acceptor, that is, as a Brensted base. And amphiprotic is used for self-ionizing solvents possessing characteristics of both Brensted acids and bases. For example, consider self-ionization of water as the solvent. In this reaction, one water molecule donates an H+. So, water is protogenic. It can act as a proton donor. Another water molecule accepts that H+ and becomes hydronium ion. So here, water acts as a proton acceptor. It is protophilic. And since water possesses characteristics of both Brensted acids and bases, it is amphiprotic. Similarly, for the self-ionization of ammonia, we can consider these terms. Ammonia is a protogenic solvent. It can donate H+ and become amide ion. Also, ammonia is protophilic because it can accept H+ and become ammonia. It is also amphiprotic because it can both act as a proton acceptor and a proton donor. It can act both as a Brensted acid and a Brensted base. Therefore, it is considered as an amphiprotic solvent. On the other hand, aprotic solvents are non-protogenic in a given situation. For example, N2O4 has nothing to do with hydrogen, with transfer of H+. So, it's an aprotic solvent. Autoprotolysis is a proton transfer reaction between two identical molecules, usually solvent molecules. In the case of amphiprotic solvents, like water and ammonia, we see that self-ionization reaction is in fact autoprotolysis. This is the autoprotolysis of water. The self-ionization reaction of water is its autoprotolysis. We have transfer of H plus between two solvent molecules. Lyonium is the cation produced by protonation or hydrogenation of a solvent molecule. Lyonium is the cation produced by adding an H plus to a solvent molecule. For example, H3O plus is the lyonium of water. NH4 plus is the lyonium of ammonia. Lyate is the anion produced by hydrogen or proton removal of a solvent molecule. For example, OH minus is the lyate of water. NH2 minus is the lyate of NH3. In other words, we can say that lyonium and lyate are general terms for characteristic cations and anions in the case of amphiprotic solvents. In the case of all solvents, we use these terms, solvonium and solvate. Solvonium is a term for characteristic cation of a self-ionizing solvent, and solvate is a term for the characteristic anion of a self-ionizing solvent. For example, NO plus is the solvonium of N2O4. Similarly, NH4 plus is the solvonium of NH3, and so on. On the other hand, NO3 minus is the solvate of N2O4. NH2 minus is the solvate of NH3. This is the end of this tutorial. I hope you find it useful.